Hey everyone, and welcome. I'm absolutely thrilled to have you here for today's explainer. Look, we hear the term machine learning thrown around constantly these days, right? But if we strip away all that dense jargon, what is it actually doing under the hood? Well, we're going to decode that magic today. And honestly, the best way to wrap our heads around this tech is to use a super relatable concept: going to school. Just picture the computer as a student sitting in a classroom, and we're going to explore exactly how machine learning acts as the framework to teach them. Okay, let's dive right into this. Because to really understand how massive of a paradigm shift machine learning is, we kind of have to look at how we used to do things. In traditional programming, a human programmer writes out very explicit rules, feeds in some data, and bam, the computer spits out a result. If A happens, do B. Pretty straightforward. But machine learning flips that entirely on its head. We literally stop giving computers the rules. Instead, we give them the raw data and the final results, the answers, basically. And we tell the machine, hey, you figure out the rules. It learns the logic entirely from experience.
Now, before we hand out the lesson plan, let's quickly clear up some terminology because, let's be honest, people use these acronyms interchangeably all the time and they really shouldn't. Think of these like nested circles. Artificial intelligence, that's the giant umbrella. It's any system trying to mimic human intelligence. Then, inside that, you've got machine learning, or ML. That's our specific subset where the machine learns from data without being explicitly programmed. And finally, tucked inside ML is deep learning, or DL. That is the highly complex, brain-inspired core using neural networks to crunch massive amounts of messy stuff, like images and text.
To really ground this, let's look at our digital student out in the wild. Because machine learning isn't just locked away in some futuristic lab. It is literally everywhere in your daily life right now. When YouTube magically knows the exact video you want to watch next, yep, that's a model that studied your watch history. Your Gmail spam filter figuring out what's junk? Machine learning. Siri and Alexa learning the nuances of your voice, self-driving cars spotting stop signs, even the face unlock on your phone. These are all models that were fed a ton of data and figured out the rules for themselves.
All right, moving on to section 1, the 3 teaching styles.
So there are 3 distinct ways we actually teach our digital students. First up is supervised learning. This is exactly like a teacher handing out a clear answer key. You give the machine the inputs plus the correct output, which we call a label. So say you feed it financial data and clearly mark whether a past loan was approved or denied. It studies those examples and learns how to predict that label for future applications. On the flip side, we have unsupervised learning. This is solo pattern matching. We hand over the inputs, but absolutely zero labels. The model isn't trying to predict a specific answer. It's just digging through the data, looking for hidden patterns, grouping similar things, or spotting weird outliers. And then we have our third style, reinforcement learning. I actually really love this quote from our source material because it hits the nail right on the head. It's essentially like training a dog. You reward good behavior and ignore or punish bad actions. In this setup, you don't give the machine the answers at all. You just let it loose to learn by trial and error. Over time, it naturally figures out which actions earn a reward, and it optimizes its behavior to rack up the highest score possible. Okay, on to section 2, preparing the lesson plan. Now, before our student can even start studying, we have to write and, well, fix the textbook they're going to learn from. And this all happens in the machine learning pipeline. It's basically the step-by-step life cycle of a real-world project. You start by defining your problem, sure, but look at step 2, exploratory data analysis, or EDA. Guys, this is pure detective work. Before you build any fancy models, you have to really visualize and understand your material. You're hunting for biases, mistakes, or weird limitations in the data, because you simply cannot clean what you don't understand. Only after that detective work do we move on to cleaning the data, actually training the model, and finally, evaluating it. And that brings us to the stark reality of what data scientists actually do all day. Just look at this number, 80%. EDA tells you what's broken, and data cleaning is how you fix it. Fixing typos in our textbook, dealing with missing values, standardizing messy categories so male and MALE mean the same thing, deleting crazy outliers. I mean, it's not glamorous work, not at all. But this vital, tedious prep work takes up roughly 80% of the time on a machine learning project. Because think about it, if the textbook is full of errors, the student is going to fail the test, no matter how much of a genius they are. Okay, so once the data is finally pristine, we let the algorithms loose. Let's look at one specific model, the decision tree. It branches out logically based on the data. But it really begs the question, when a computer is staring at a massive spreadsheet, how does it actually think? How does it decide which feature or which column is the absolute best one to split its decisions on first? Now, what's really interesting here is just how purely mathematical this whole process is. The computer calculates something called entropy, which is basically the amount of chaos or disorder in the data. It then tests every single feature to see which one reduces that chaos the most, a metric known as information gain. So looking at outlook, temperature, humidity, and wind, the math shows that splitting the data by outlook gives us the highest information gain at 0.246. Boom. Mathematically, outlook becomes the root node, the starting point of the tree, and it just recursively branches down from there.
But hey, not all algorithms use trees. Take k nearest neighbors, or KNN for short. This is a totally different learning style. When you ask KNN to classify a brand new piece of data, this particular student basically just cheats off its closest peers. It calculates the actual mathematical distance to the other data points, finds its k closest neighbors, and just takes a majority vote. Simple as that. If most of the neighbors closest to it are labeled yes, it confidently predicts yes. It's spatial, it's super simple, and it's surprisingly effective.
But wait, how many neighbors should our student actually look at? Well, that is where hyperparameter tuning comes into play. This is basically us tweaking the student's study settings. We test out different k values to see what performs best on unseen data. Check this out. If we only look at one single neighbor, our accuracy is a pretty dismal 60%. But if we just expand our view to k equals 5, our accuracy skyrockets to 92%. Oh, and quick tip. We almost always use an odd number, like 3 or 5, just to make sure we never end up with a tie in that majority vote. All right, that brings us to Section 3, the final exam and teamwork. So our models have studied their pristine data, they've tuned their settings, and now it's time to grade them and see what happens when we group them together. And when we're grading this final exam, we definitely do not just look at overall accuracy. Why? Because out in the real world, different mistakes carry very different costs. So we rely heavily on precision and recall. Precision is your go-to when false positives are a nightmare, like a spam filter wrongly throwing your boss's email into the junk folder. Recall, on the flip side, is absolutely critical when false negatives are the danger, like a medical AI completely missing a disease in a sick patient. You've got to choose the right grading metric for the exact problem you're solving.
And while we're grading, we are constantly battling the bias-variance trade-off. On one extreme, you have high bias. This is underfitting. Basically, this is the slacker student who glanced at the textbook for 5 minutes and completely fails the test because their understanding is just way too simplistic. On the other extreme, high variance. This is overfitting. This is the student who literally memorized the practice test word for word. They look like a genius until they see new, slightly different questions on the real exam, and they completely freeze up and fail. What we're desperately looking for is that perfect middle ground. So the crucial point is, how do we actually guarantee we hit that perfect middle ground? The secret weapon is ensemble learning. The whole philosophy here is we hear the crowd. Instead of putting all our faith in one single student model who might slack off or overthink things, we combine multiple models and let them vote or average out their answers. A whole group of models working together is inherently smarter, way more stable, and much more accurate than a lone wolf, helping us finally achieve that holy grail: low bias and low variance.
And this brilliantly illustrates the two main strategies we use to build these teams: bagging and boosting. Bagging trains multiple models at the same time, in parallel, on random chunks of data. Think of a random forest. And they all vote independently. Boosting, though, that's sequential. Every single new model is built for one specific purpose: to correct the exact mistakes made by the model right before it. Algorithms like XGBoost use boosting, and let me tell you, they are absolute industry favorites right now because they aggressively learn from their own errors until that final prediction is razor sharp. Which really leads us to one massive, overarching thought to wrap up on. We've just seen how machines take in data, figure out their own rules, meticulously tune their settings, and even work in sequential teams to aggressively correct their own mistakes. If simple machine learning algorithms can already mimic this much of how we learn, as we push even further into the complex neural networks of deep learning, just how much closer are we getting to true human cognition? It is a wild, fascinating question to ponder as this tech just keeps evolving at breakneck speed. Thank you so much for hanging out with me for this explainer. I really hope it gave you some concrete clarity on how the machines all around us are actually learning.